we present transient neural radiance fields, a method for novel view synthesis of Lidar measurements and 3D reconstruction. Transient NERF takes as input raw, time-resolved photon count histograms measured by a single photon Lidar system from multiple viewpoints. These measurements capture the time of arrival of photons from the laser pulse, which we bin into a photon count histogram. Playing the captured measurements of the scene back over time reveals the picosecond scale video of a pulse of light traveling to a scene point and back, as captured by a single photon Lidar system. Our method renders these time-resolved Lidar measurements from novel views. We demonstrate this capability for this scene captured with our prototype single photon Lidar. Our method is the first to explore novel view synthesis of the picosecond scale transient light transport phenomena captured by a Lidar system, and may be especially useful for applications that seek to simulate raw Lidar measurements for downstream tasks in autonomous driving, robotics, and remote sensing. Our work built on neural radiance fields, which have become a ubiquitous tool for modeling scene appearance and geometry for multi-view imagery. Recent NERF-based methods, such as depth-supervised NERF, urban NERF, or time-of-flight radiance fields, also explore using LiDAR or depth sensor measurements. However, DS-NERF and urban NERF focus on rendering RGB images and use LiDAR-derived point cloud data only as auxiliary supervision. TERF incorporates measurements from time-of-flight sensors, which are distinct from LiDAR. Thus, none of these measurements incorporate the underlying image formation model of the LiDAR or render LiDAR measurements from novel views. Our method uses an efficient neural representation with a hashing-based feature grid to parameterize the radiance and density of a scene. To synthesize a novel LiDAR view, we query the neural representation at points along a ray corresponding to a pixel coordinate in the LiDAR image. We then use the network outputs alongside our rendering equation, which produces time-resolved measurements of light transport in the scene. Our rendering equation models LiDAR image formation, including the shape of the laser pulse and radiometric falloff effects, and we supervise on time-resolved photon count histograms from multi-view LiDAR scans. We train the network on a new multi-view dataset of simulated LiDAR measurements we create using scenes from the NERF Blender dataset with a modified version of the Mitsuba 2 renderer. After training, we render out novel views of LiDAR measurements. By integrating the transient measurements over time, we can recover a conventional image similar to other NERF methods such as DS-NERF or urban NERF. Our method allows recovering relatively high-quality models of scene appearance and geometry after training on only a few input views. Compared to DS-NERF and urban NERF, our method avoids supervision on point clouds obtained by potentially noisy and thus view inconsistent per pixel estimates of depth. Instead, we train on raw photon count histograms and optimize for a representation that best explains measurements captured across all views, resulting in much higher geometric accuracy as shown in the paper. We also test our method on a dataset we capture using our prototype single photon LiDAR system shown on the left. The hardware system contains a picosecond laser that shares an optical path with a single photon avalanche diode. We scan the scene using a 2-axis scanning galvanometer. The scenes are mounted on a rotation stage to facilitate multi-view scanning. We also test our method on a dataset we capture using our prototype LiDAR system. The dataset consists of 6 scenes captured from 20 different viewpoints each using the prototype single photon LiDAR. Our method enables rendering of novel LiDAR views after training on captured data. Finally, we also show view synthesis of intensity images obtained by integrating the LiDAR measurements over time after training on 2, 3, and 5 views. Overall, our work brings NERFs to a new dimension of imaging at picosecond timescales, newly enabling rendering of transient imagery from novel views.